Continuing our discussion of how the derivative can have an impact on the shape of a graph, next question to pose would be, what can a second derivative tell us about a graph? What I'd like to do is consider two situations. Here's a t-axis and a position function, and a t-axis and a position function. Suppose you're in your car. Your car is at a stoplight turns green, you slam on the accelerator. How far have you traveled over the course of time if you are accelerating? Chances are pretty good you would start off pretty slow, but then you would be speeding up and speeding up and speeding up. Now, another situation is you're driving in your car and you see a red light, and as a result, you slam on your brake. Now, as you slam on your brake, you're already going pretty fast, and you'll be slowing down and slowing down and slowing down. And in both of these situations, the distance traveled is increasing. I can tell that we are increasing because if we take a look at the slope of a tangent line, slope of the tangent line is going to be positive all the way through here. Now, here is the difference between these two situations, and it has to deal with how the curve is curving. In both of these situations, it's increasing because as we go to the right, we're going in the upward direction, but we're increasing in very different fashions. You'll notice that if I were to draw in additional tangent lines on the first curve, the slope of the tangent line is getting bigger. So what we can say in the first situation is that f prime is increasing. The slope of the tangent line is getting bigger as we move to the right. Whereas if we were to look at the second situation, the slope of the tangent line is actually getting smaller. The lines are getting flatter. So in that regard, what we're saying is that the slope of the tangent line is getting smaller. That is to say, it is decreasing. Now, the way that we analyze whether something is increasing or decreasing is by saying whether the derivative of that thing is positive or negative. So the derivative of the derivative, if the derivative is increasing, that means that the derivative of the derivative is positive. That is where we can see a second derivative. Whereas if the derivative is decreasing, then that means that the derivative of the derivative would be negative. I just realized that I said greater than 0 over here and negative over here, so I'm going to fix it. So f double prime is positive, and over here we're saying that f double prime is less than 0. This introduces the idea of concavity. Concavity is the rate at which the rate of change changes. It is the rate at which the rate of change changes. Now, the two situations that we have, if the rate at which the rate of change is changing is positive, that means that the first derivative is increasing. That means that that situation is referred to as concave up. If something is concave up, we are expressing that as the second derivative is greater than 0. The other thing about concave up is that you'll notice that all of these tangent lines that we have in green, they're all below the function. So the function itself is on the top side, which is why we call it up. Now, in the second situation over here, the rate at which the rate of change is changing is decreasing, or negative, I suppose. The tangent lines are all above the given curve. In this case, we would say that the function is concave down. So that's where the second derivative is negative, or less than 0. Now, when you put these things together, you will get what is known as inflection points, or intervals of concavity. So intervals of concavity will work basically the same way as determining intervals of increase and decrease, except we'll be dealing with f double prime. So set f double prime of x equal to 0 and test those intervals. Now, when you have a function that is either increasing or decreasing, points where it changes from increasing to decreasing or from decreasing to increasing are known as local extreme points, so local maxima and local minimum. So points where the inflection changes, where the concavity changes, are called inflection points, or points of inflection. Now, generally, those occur where the second derivative is equal to 0, but it doesn't always necessarily have to happen that way. Now, another way to think about concavity is, suppose that what you're actually looking at here is a map, and the function drawn is the path of a car that is traveling. In the first situation, if you wanted to travel along this path, in order to maintain yourself on this path, you would have to be turning your steering wheel slightly to the left in order to make sure that you are going along this path. Whereas if seen from above, this is the path from a car, you would be turning your steering wheel slightly to the right to maintain this kind of thing. An inflection point is where you're changing the steering wheel from turning to the left to turning to the right, or turning from the right to turning to the left. Basically, it's a point on a curve where you see that something is kind of straight in its travel. So the portion that I'm referring to that's kind of straight would be this point right here. At this point, we're changing from turning the steering wheel to the right to turning the steering wheel to the left. The other way to think about inflection is, if you were to curve your fingers in the same direction as a curve, check to see which direction your palm faces. If I were to put my fingers in the same direction as this curve, you'll notice that my palm is facing in the upward direction. Therefore, this would be considered concave up. Whereas over here, if I were to curve my fingers in the same direction as the curve, my palm is facing in the downward direction. Therefore, we would call that concave down. So next, let's work through some examples where we actually calculate these intervals of concavity.